Okay, say if we're looking at finding out the function and the corresponding power series representation of what we have for the differential equations that we have listed. And first of all, we have y prime plus 7y is equal to 0. And looking at what we have in terms of Maple, okay, so we're going to go to what's referred to as the ODE Analyzer Assistant. So we're going to go into worksheet mode on this one, okay. And what we're going to do to kick things off is highlight Tools, go to Tutors, and some versions might have it under Assistance. But if we go to Tutors, okay, so we'll go to Differential Equations and go to ODE Analyzer Assistant, and you're going to have this item to show up. And if we look at solving, okay, first of all, for y prime plus 7y is equal to 0, if we go to Edit, and you're going to go to Assist, okay, so we have inserting the derivative of y with respect to x of the first order, insert, click on Done, and for adding 7 times y, so you have plus 7 times, and you have to enter the star, and for y, it's going to be y with respect to x, so you're going to have to enter y sub x, and we have is equal to 0, and if you're satisfied, you can click on Add, so you got y prime plus 7y is equal to 0, and once you are done, you can now look at solving symbolically, and looking at the series solution from Maple. Again, you click on the circle next to formal series, click on Solve, and you're going to have this particular display. And we're going to put this in terms of the power series representation, where we have factorial notation as opposed to gamma notation. And if we look at, say, for the second function, and I'm just going to delete this first equation, and if we look at y double prime plus 25y is equal to 0. So now we have for assist, now we got y with respect to x of the second order, insert, and we have plus 25 times y of x, and we have is equal to 0. And if I add, and everything looks good, you can click on Done. And like the first, we solve symbolically, and again go with formal series, press Solve, and we have this set of expressions with the factorial notation. And again, we're going to clean this up. And if we look at what we have for the next item, and so if we go to Edit, and I can just delete this equation, and for the next second order differential equation, so again, go to Assist, insert derivative of y with respect to x of order 2, insert, and we have minus 30 times y of x is equal to 0. Click on Add, and then Done. Solve symbolically, go with formal series, solve, and we have this set of terms to appear. And now for what we have in the case of the third order differential equation, so if I edit out what I have here, delete, then go to Assist, now we have y with respect to x of third order, insert, and then we have plus 100 times, again, Assist, so you have y with respect to x of order 2, insert, and so we have this sum of expressions equal to 0. And if I add, click on Done, solve symbolically, again, go with the formal series, solve, and we have this set of expressions. Okay, so from the first equation for y prime plus 7y is equal to 0, okay, this was the response that we got from Maple. And just to clean up the notation, so we got with negative 7 to the n times x to the n. That is going to be the quantity of negative 7x raised to the n. And for the gamma function, you have gamma of n plus 1, and that's going to be equal to the factorial of the expression that is going to be 1 less. Okay, so in this case, gamma of n plus 1, that is equal to n factorial. So for the power series representation, so we have y of x is equal to c of 1 times the summation as n goes from 0 to infinity. Again, we have of the quantity of negative 7x raised to the nth power over n factorial, and that is equal to the constant times e raised to the negative 7x, and that will be the final result in this one. Okay, for the second differential equation, this is what we had in Maple, and I'm going to have to make some adjustments to what we have in the numerator and denominator. So just cleaning up what we have in the exponents and converting from gamma to factorial notation. Okay, so for what we have in the first summation, negative 25 to the n times x to the 2n. Okay, if I draw out the negative, so I have negative 1 to the n. Now for 25, 25 is going to be the square of 5. So like we have for 5 squared to the nth power, that's going to be the same as 5 raised to the 2n. And so I got 5 to the 2n, and notice we have x is already raised to the 2nth degree, and consolidating we have, in this numerator, we have negative 1 raised to the n times the quantity of 5x to the 2nth power. And for the gamma function, we have gamma of 2n plus 1 is equal to 2n factorial. Now, where we have the degree to be 2n plus 1, now for 25 to the nth power times x to the 2n plus 1, again, history repeating itself. We have negative 1 to the n, and now, again, 25 is the square of 5, and 25 would be 5 to the 2n. But if I write 5 to the 2n in terms of 5 to the 2n plus 1, I'm going to be looking at sacrificing a 5 just to keep things in balance. And we have multiplying x to the 2n plus 1. So we have 1/5 of negative 1 to the n times the quantity of 5 times x raised to the 2n plus 1 power. And for the gamma function, we have gamma of 2n plus 2, and that is equal to the factorial of the quantity of 2n plus 1. And so for what we have in terms of the power series representation, so we got c sub 1, and you have times the summation as n goes from 0 to infinity, and we have a negative 1 to the n times the quantity of 5x to the 2nth power all over 2n factorial, and we have plus c sub 2 over 5. And we can say we have a constant over constant. It's still a constant, so we can call this alpha, or we can leave it as c sub 2 over 5. And we have times the summation, again, of negative 1 to the n times the quantity of 5x to the 2n plus 1 power all over 2n plus 1 factorial. And for what we have in terms of the functions, the first summation will be in reference to the cosine of 5x. So you have c sub 1 times the cosine of 5x, and we have plus 1/5 of c sub 2, or in this case, we can say we have alpha, and this next summation will be in reference to the sine of 5x. And so we have both the function and the power series representation of the equation that we have in number 2. Okay, so for what we have in this one, okay, so we have a bit of cleaning up to do with the powers in the numerator of both summations, as well as converting from the gamma function notation to the factorial. Okay, so looking at what we have Okay, for the first summation, you have 30 to the n times x to the 2n, and if I consolidate, expressing in terms of the 2nth degree, well, 30, not a perfect square number in the integers, but 30 is going to be the square of the square root of 30. So in consolidating, we have the square root of 30 times x, quantity to the 2nth degree. Gamma of 2n plus 1, again, that is going to be the factorial of 2n. Now, expressing the numerator in the second summation in terms of the 2n plus 1 degree, well, for 30 to the n, you still have the square root of 30 to the 2nth power, but if I express the square root of 30 in terms of the 2n plus 1 degree, that means I'm going to have to kind of do a little bit of a sacrifice. So to raise in terms of plus 1, I'm going to have to express this as 1 over the square root of 30 times that radical expression to the 2n plus 1 power. And again, we have times x to the 2n plus 1. So we have in consolidating, we have 1 over the square root of 30 times, again, x times the square root of 30, all raised to the 2n plus 1 power. And for gamma of 2n plus 2, that is equal to the factorial of 2n plus 1. And just writing upon converting. So we have y of x is equal to c sub 1 times, again, you have the square root of 30x raised to the 2nth power all over 2n factorial, and you have plus 1 over the square root of 30 c sub 2, and by then you can just either leave it as it is, or you could write this as another constant, where you have a constant multiplied by a constant is still a constant, and we have times the summation of the square root of 30x, 30 times x, and we have raised to the 2n plus 1 all over 2n plus 1 factorial. And we have for the function, so we have c sub 1 times the cosine of, you can say x times the square root of 30 or the square root of 30 times x. But again, x is going to be outside the radical. And we have plus, and we'll say we have alpha times the sine of the same angle, where we have with the square root of 30, and then we have times x, and that will be the layout of what we have with this third differential equation. And for what we have in the remainder, so we have in the remaining differential equation, again, this is what we have in the layout from Maple. And there'll be a few twists on this one, but I'm going to clean up what I have in the summation. Okay, so for what we have here in the numerator within the summation, we have negative 100 to the n times x to the n, and that will consolidate to the quantity of negative 100x raised to the nth power. And again, gamma of n plus 1 is equal to n factorial. And looking at what we have in carrying over to y of x, okay, notice we have, upon expanding, so we have c sub 1 plus c sub 2x, and we have plus c sub 3 times the quantity of negative 100x raised to the nth power all over n factorial. And following this summation, we have 100 c sub 3x minus c sub 3. And I just want to mention, notice the standalone constants. We have c sub 1 minus c sub 3. We can combine those and say we have alpha. And for what we have in the case of our x terms, so we have c sub 2x plus 100 c sub 3x. And I can just consolidate this as beta times x. And so in the rewrite, I'm going to have that y of x is equal to alpha plus beta x plus c sub 3 times our summation. So this is what we have in the power series representation. And for what we have in the case of the defining function, so we have for y of x, we have alpha, again, plus beta x, and then we're going to have plus c sub 3 times e to the negative 100x. And that will be the final result.